theory, materials design, and related subjects in the country. And he gives excellent pedagogical lectures. So I think one is ideally placed to hear this colloquium in the evening. Let me just quickly introduce him, though I think most of you would be knowing him, but just for the younger students. So Professor G.P. Das is a condensed matter physicist and material scientist, and is very well known for his pioneering works in electronic structure and materials design. He's made very important contributions to a wide range of problems in condensed matter physics, and is therefore ideally placed to sort of give this colloquium. He's been at the best places in the country. He started off, I think, in BRC Mumbai. Then he was a senior professor at IICS Calcutta, which is where I first had the good fortune of meeting him. He was visiting professor at IIT Kharagpur for several years, and now is at TG Crest in Kolkata. He's also spent many years visiting departments overseas, and has had sort of a wide range of collaborations with some of the best people in the field. I just want to emphasize one thing, that in the course of his long journey in physics, he's received many recognitions for his research contributions, and has spearheaded many research programs both nationally and internationally. Okay, so in particular, he has recently been given a Lifetime Achievement Award by the Asian Consortium for Computational Material Science. So that's something very sort of prestigious. But of course, I always remember GP, as we fondly call him, as an inspirer of many generations of material scientists and DFT specialists in the country. So without further ado, I request Professor G.P. Das. He's going to talk about the modeling interfaces in materials and devices, merging DFT with machine learning. Please.
So first of all, thanks to my old friend Sanjay Puri for the generous introduction, and I must thank Satyabrata Brijesh and the entire team for inviting me to this beautiful conference, and particularly for giving me this opportunity to give this talk. Well, I mean, it's this talk I have decided specifically aim at students, because this is a conference where I see quite a substantial number of young students, young researchers, which is very encouraging, I must say that. And so I decided, when I was first asked by Satyabrata to give this talk, I thought that at what level I will handle this. Then I thought that no, it should be mainly aimed at the students. And of course, there are, specialists, the senior people, who probably will be generous enough to excuse me for that. Okay, now, one thing I would like to say, that there are many technical details which I will avoid. Anyway, you are always welcome to get it straightened out by writing to me or whatever. And the other thing is that, in this particular conference, there are various kinds of talks, very impressive talks, starting from 2D materials to spintronics to orbitronics to topological materials, Berry phase, and whatnot. All kinds of things have been discussed by different people in course of the past 3 days, and I thought that I will talk about the manifestation of quantum effects at the interface. Okay, which is, as you will see, it is very important in materials as well as in devices. Okay, so that's the very purpose of my talk here. And these the interfaces are really very tricky things, because it's buried. It's not surface, it's interface. So interface between two dissimilar solids, it's buried. And as a result, to extract quantitatively relevant information from a buried interface is quite often non-trivial. More so in such cases where there are interfaces which are dynamically evolving. What do I mean by that? Let's say, for example, in batteries, I'll try to devote some time towards the end of my talk on batteries. There, the interface is dynamically evolving. So how is it possible for us to do the statics as well as dynamics, the molecular dynamics, okay, of such kind of interfaces? And the last comment I would like to make before I start my talk is that, the band structure, the bands, accurate bands is something which is very, very important to handle these kinds of systems. When I talk about bands, it has to be, as you know, that it can be at various levels of sophistication. You have to include, in many cases, the spin orbit coupling. You have to include probably the Hubbard U, the spin textures, and many, many things. So, all said and done, unless we have got the right kind of bands in front of us, it is not possible for us to really, do justice to these interfaces. So let us start by giving a 1 or 2 slide introduction on, because it is a quantum material conference, so I have to tell something about the happenings in condensed matter physics in 21st century. I can say without any hesitation that condensed matter physics is one of the most happening field in science. So these are things which all of you know. I mean, discovery of graphene, then the Dirac materials, which there is a quasi-particle zoo, which is a Dirac, while Majorana fermions, then 3D topologically ordered states, quantum spin Hall effect, anomalous Hall effect, twistronics, spintronics, etc., etc. This is definitely not an exhaustive list, but these are all, if you can see, happenings of the 21st century condensed matter physics. And I would like to tell you, the students, that there are 2 disruptive discoveries which have taken place, namely, which has given the paradigm shift in our understanding. One is the discovery of quantum Hall effect in 1980 by von Klitzing, and that is what marked the advent of topology in condensed matter physics. And the second one is in 2004 by Gaiman Novoselov, the discovery of graphene, which is the first Dirac material in action. Okay, so these 2 are the disruptive discoveries in the field of quantum condensed matter physics during the past decades. So if you look at the history of the quantum materials from the 1980s, I keep 1980 as the thing because that is the discovery of quantum Hall effect. From 1980s to present to future, okay. So 1980s, of course, the quantum Hall physics, okay, and the high TC superconductor, of course, which we have seen. I remember the euphoria of the high TC superconductors in 1970s. 80s. Okay, then in 1990s we have the topological Berry phase and the new particle fractionalization. Okay, the composite fermion. You have already heard a fantastic talk by Gyanendra Jain, and many advents of nanoscale physics. Today, present, the topological insulators, spintronics, multiferroics. Again, many of the talks we have listened to, and of course, cold atoms, advanced spectroscopies, and nano devices, etc., etc. Future, quantum computation. We are doing a lot, but a large chunk is still remaining to be seen. Okay, quantum computation and cryptography, topological electronics. It was mentioned in some of the talks that are we really in a position that we can say, okay, silicon age is over and we are going to the topological electronics? The question is something which is for you guys to answer. Okay. And of course, above room temperature superconductivity, motronics, etc., etc. So these are this is the chronological this thing, and the properties of the quantum materials. Okay, all of these we know to a large extent, namely the quantum confinement effect. I don't want to go through the list. The strong electron correlations and the topology and symmetry. Okay, now what is this talk in a nutshell? So in one slide, I will tell you what is it that I am going to talk about in this presentation. Okay, first of all, the focus on quantum effects that appear at the interface between two solids, that confining electrons in 2D plane forces novel properties to emerge that neither of the bulk materials have. So we have got a completely new property at the interface. In a semiconductor heterojunction, that is what I will start with, or a metal semiconductor interface, the abrupt change in crystalline structure, band alignment, or electrostatic potential that traps the charge carriers in a very thin region, forming a 2D electron gas. Okay, and this allows some extraordinarily high electron mobility, leading to discovery of the the integral and fractional quantum Hall effects, and many other things. Now there are manifestations of many more interesting effects at the interface. There are quantum effects and there are things which are beyond quantum effects, which I will try to point out, that are crucial for device performance. One is Schottky barrier height. I'll tell you because I myself have some experience on Schottky barrier height, which I'll try to share with you, that are crucially important in semiconductor devices. 2D materials, okay, heterojunction. This also, there were talks on this, okay. The van der Waals, so-called, the van der Waals heterostructures, okay. One has the freedom of matching materials that have very different structural and electronic properties, and ultimately resulting into some novel devices which we are experiencing today, 2D and quasi-2D materials. And finally, in energy devices, namely such as solid-state batteries, where the anode and the cathode are electronic insulators but ionic conductors. Very interesting, okay, systems from a condensed matter physics point of view. And the solid electrolyte actually is the one which drives the game. Okay, I will tell you a little bit more in course of my talk. So it is the solid electrolyte that drives the game via the electrolyte again interface. The interface between electrode and electrolyte that are notoriously complex to handle. Okay, and I will tell you why am I saying that it is notoriously complex with all kinds of defects, grain boundaries built in. So you see, from the beginning to end, I'm talking everywhere about different kinds of interfaces in different levels of sophistication. Now I will tell you that let's devote some time on the tools that we have to use the right kind of tools in order to unearth the details of the physics. So what are the tools? DFT and beyond DFT. Okay, let's talk about the epitaxial. I'm sure you know what is epitaxial interface. Okay, intimate interface. A ends, B begins, and there is a very well-defined space group, you can say, of the AB junction. Okay, so the structural, electronic, and magnetic properties are something which are being investigated for the past several decades. Okay, so the physical quantity that is extracted depends on the type of interface. For example, if it is a metal semiconductor interface, Schottky barrier. Semiconductor heterojunctions, band offset. Insulator semiconductor, the interface states. Metal ceramic joints, chemical bonding. Ferromagnet, non-magnet, ferromagnet, metallic multilayer, GMR. Ferromagnet semiconductor, spintronics. So you see, it depends on the type of interface, what physical quantity is of relevance. And interestingly, density functional theory based approach using supercell geometry provides a unified framework to handle all these different kinds of interfaces using one general tool, which is DFT. Okay, this is not a lecture on DFT. So, I mean, as all of us know, that density functional theory is arguably the most successful and promising approach for first principles investigation. And basically, this is what is called the DFT total energy functional, which I'm sure the students all know it. Okay, so essentially what DFT does, it decodes the underlying physics of many of the novel materials phenomena. For example, 2D systems, Moire pattern, topological insulators, spintronics materials, etc., etc. Essentially by mapping the intricate electronic structure of a many electron problem to a self-consistent one electron problem, which is solved with a high degree of precision. This is in one shot what is done in a DFT. But interestingly, it plays an indispensable role in quantum materials for three primary objectives. What are those? Understanding, interpretation, and predictive capability. These are the three most important things. Okay, so nature came up with, this is in 2014, a little bit old, but it came up with the top 100 papers, and I don't want to go into details, but the 12 of the top 100 most cited papers pertain to DFT. So those of you who are interested, you can see this nature. Now I tell you, once I being involved in DFT for the past so many decades, more recently, when I found that the machine learning has started, playing a crucial, critical role, then I was thinking that the impact of quantum modeling in material science, does machine learning have any role? So this is a question. Now, can deep learning accelerate the discovery and design of quantum material? This is a question. Answer, it is for us to decide. This is a paper which is approximately about 7-8 years old. Unimaginably large number of citations. The paper is named "Attention is All You Need." I'm sure that there are people who are doing machine learning, they all know this paper. And this paper is Vaswani et al. It demonstrates the deep learning model based transformer architecture. Transformer architecture is something which is very, very popular. And this is one of the highest cited paper in AI/ML, and the citation is something which is just going beyond all imaginations. So why I said that in the previous slide, I showed you about the DFT things, but now I am surprised to see that these are the things which are now peeping in, okay? Anyway, so we know that DFT has its own limitations, driving a series of improved ramifications. And these are things which we all know. We know what are the limitations of DFT. For example, we know that it does not give the band gap properly. The consham orbitals are only for the exact ground state, not for the excited state. We know that the strong or intermediate correlated systems such as transition metal oxides need explicit account of correlation via Hubbard U. Most of the students, they routinely use in their simulation that LDA plus U or GGA plus U or whatever. That U is nothing but that Hubbard U, okay, in the model Hamiltonian approach. So, and then, for example, things like, van der Waals interaction, is something which per se is not included in the DFT. So we introduce what is known as the dispersion correction. So there are many of these things which we know are the limitations of DFT, but we also know how to overcome it, okay? So the accuracy which is achievable in DFT calculation is inversely proportional to the system size, which is n. Now in DFT, it goes as n cube. Sometimes it is better, it is n log n, or even better, which is linear scaling, proportional to n. N is the number of atoms in the supercell or the unit cell. But that depends, that accuracy which is achievable and the scaling, it depends on the basis set. Whether you are using a plane wave basis set or a localized basis set or an augmented basis set, and so on and so forth, okay? So in workshops on density functional theory, we give details about this, but here not. The question is, can we overcome this size restriction of being able to handle only about something like ballpark 1,000 atoms, okay, today, with today's computer, okay, maximum about 1,000 atoms we can handle. But 1,000 atom is what? 1 nanometer, 1 nanometer, 1 nanometer, if you see a cube roughly. So we get 1,000 atoms. Now, experimentalists are not happy. So the demand is for DFT to be able to handle a more realistic length scale which is achievable in experiment. So the experimentalists are demanding more. So the answer has been provided by some recent developments in using finite element basis, which we call it DFT FE. FE stands for finite element, that can successfully handle of the order of 100,000 electrons. And most important is the last line, without sacrificing the accuracy. Today we can do it. And I'll give you just one example before passing on to the interfaces. Large-scale materials modeling with a quantum accuracy, DFT FE, okay, breaking through the barrier on accuracy length scale trade-off in ab initio methods. Now, this is something which has been done by my collaborator Fani Motamari in IISc Bangalore, and this is open source code, and it is all available, okay, open source. Okay, so basically it's a polynomial. Well, I'll tell you. The challenge is I cannot go into the details except to tell you the essential. The Germans call it Schwerpunkt. So the main things, challenge, accurate large-scale Kohn-Sham density functional theory calculations for generic material systems are prohibitively expensive due to asymptotic cubic scaling complexity of DFT with a number of electrons. The solution is to resort to a real space formulation with a systematically convergent finite element basis. Polynomial basis we do it, okay? So the current state of the art real space finite element based methods have been implemented in DFT-FE. And the capabilities of this is something which is really impressive. It can handle a fully periodic. One example I will tell, and then one example which we have done recently, and that is this is actually an example from material science. The large-scale DFT calculation with finite element basis has been successfully deployed to study chemisorption of hydrogen in silicon nanoclusters. I have been working with my students in ISCS a lot on hydrogen storage. So this is something where very quickly I will tell you that if you take a silicon nanocluster, okay, and hydrogenate it, the hydrogens will go and put on the dangling bond of silicons, okay, fine. Now, what you do is that you put some carbon alloy, nano alloying the silicon cluster with carbon. If you do that, as you know that the carbon distances, being lesser than silicon, they will automatically go to the center. Okay, even if you do molecular dynamics, you will see that it will go to the center. And what will happen is that the hydrogens which are all around that, those and the silicons on the outer side, they will get affected by this carbon alloying in such a way that the hydrogen-hydrogen dimer formation will take place. And it will take place more and more if you increase the number of size of the silicon carbon nanocluster. If you take this as a motif, okay, one-fold, make it two-fold, five-fold, 10-fold, 20-fold. I have not shown all. This is a 20-fold thing of this. So this is 20 times this. So naturally, you can see the number of atoms becomes huge. And look at that. Si 120, C25, H 150. It's a huge. And if you do that, then we really find that the hydrogen dimerization is helped. And unless the hydrogens dimerize, we cannot use it for the purpose of hydrogen storage. Remember that in hydrogen storage, the hydrogen in a nascent H form is of no use. It has to be H2. So that is what was our aim. The original idea, I must say, that was first given by Giulia Galli way back in 2004. But at that time, there was no way that a density functional calculation could be done in such a magnitude. We have done that. And this paper was published in JCTC, the chemical bonding in large systems using projected orbital and Hamilton population analysis with finite element based DFT calculation. So this is one example which I gave you, and just for your information, even though I have not shown, we have tried to do this using the standard plane wave code like quantum espresso. We failed. Quantum espresso could go up to 5-fold, up to 10-fold. But when we went to 20-fold, it just conked off. In the best possible computer in our country, we could not do it. Okay? So, plane wave raises the hand. And there the finite element comes, and we could get that. There are details which are available. Those of you who are interested, you can see that. So, the moral of the story, if you want to do a DFT calculation in 100,000 atoms, electrons, okay, without sacrificing the accuracy, think about going to finite element basis rather than a plane wave basis, which 90% of the students, they use it. For details, you can always contact us, here. And this is all developed indigenously. Okay, so back to epitaxial interfaces. That's our subject matter. Okay, so first thing which comes is the semiconductor band offset. Very simple. Aluminium arsenide, gallium arsenide, aluminium arsenide. This is semiconductor heterojunction, where, as you know, gallium arsenide has got lower band gap, aluminium arsenide larger band gap. So there is a conduction band offset and valence band offset, which is defined like this. Very simple. Okay. The valence band offset is the semiconductor 2 minus semiconductor 1, the valence band, and the conduction band is simple. Okay. Now, at least 100 to 200 papers have come out on this in this, and I have just summarized it. And let me just tell you show you one picture here. This is the band offset, the valence band offset, which is obtained by density functional theory, and this is the experiment. Okay, and look, almost all the dots, they fall on the 45-degree angle, which means the density functional results matches with the experimental result pretty well, excepting there are some bad boys of the game, like for example gallium phosphide silicon or zinc selenoid germanium and things like that. But otherwise it almost all falls on this 45-degree angle, which shows that DFT really is successful for predicting the band offset in epitaxial semiconductor heterojunction. Okay, the other details are there, and these are all available in the literature. Now, I wrote way back a review in Pramana in 1992 on electronic structure of epitaxial interfaces. Here, I discussed in great details all kinds of semiconductor and semiconductor metal epitaxial systems. I did it. This was at that time I was in BARC. You can see that what Sanjay told. You know. So at that time I was in BARC, but more recently, we did something more, which I will try to touch upon, on the manifestation of interface-induced effects in 2D MSI to SI111 quantum heterostructures with one of my students, Abdul, and that was sometimes, well, when? It was in something like 2022, okay? So here there are some much more details which are there from the more recent results that we have. Okay, now the metal semiconductor epitaxial junctions, I would like to tell you that it's a 2D quantum structures, and it's the fundamental constituents of electronic devices. The most important things as far as the physics of these quantum devices are concerned are given here: 1, 2, 3, 4, 5. Localized surface and interface states. The surface states evolve due to presence of unsaturated dangling bond at the surface. And interface states are nothing but the surface states of a semiconductor substrate in presence of an overlayer. Metal-induced gap states. Volker Heine talked about this in 60s. Okay, so the evolution of the localized states that due to spilling over of the electronic states from the metal Fermi level Fermi C to the semiconductor band gap. The work function of a metal overlayer. Okay, which is a surface property. There is a minimum amount of energy required to remove an electron from Fermi level to infinity, which is work function. P-type Schottky barrier height. Okay, why P-type? I'll come to. The energy difference between the Fermi level of the metal and the valence band top of the semiconductor. There is a reason why I'm talking about the P-type, because, okay, let me wait for the next slide to come. And the Fermi level pinning, that is Schottky barrier height, is found to be nearly independent of the choice of the metal. This is something which is very interesting. Every metal has got different work functions that we all know. When the work functions are varying by EVs, the Schottky barrier height are not varying even by milli-EVs. Why? We still did not understand in those days. So, P-type Schottky barrier height is nothing but the Fermi level minus the valence band top. So, why we are interested in the P-type Schottky barrier height? Because here both these quantities are occupied part, and LD, density functional theory, can tell us, give us a good accurate of the occupied part. Now, if you talk about the N-type Schottky barrier height, it is the conduction band bottom minus the Fermi level. Now, conduction band bottom, if you want to see, then you know that it is the excited state property, and density functional theory cannot be taken that seriously. That is why what we do is that we always calculate the P-type Schottky barrier height and then subtract it from the gap and get the N-type Schottky barrier height. And of course, the work function is known, the E vacuum minus EF. Now, particularly, the system nickel disilicide on silicon was chosen by us long back, which is, here you can see the high resolution cross-sectional transmission electron microscopy, and look at the intimate interface. I mean, nickel disilicide ends and silicon begins, or silicon ends and nickel disilicide begins. There is hardly anything in between. It is called the intimate epitaxial interface, and this was first done by us way back in 89 when I was in Max Planck Institute. So Ole Anderson, Peter Blechel, Christensen, Gunnarsson, and we all wrote this paper, which took us more than a year to write. Okay. Now, when we talk about the metal disilicide silicon interface, it is very crucial as to what is the coordination at the interface. How is the nickel, the nickel of the nickel disilicide, that is the metal, how is that coordinated with that of the silicon? This is silicon 111 and this is nickel disilicide. This is called 5-fold coordinated. This is 7-fold coordinated. That is very simple. What do you mean by 7-fold coordinated? That how many silicons are there which are coordinated with the nickel. Nickel is the blue one. Okay. So here it is 5. You can see that. You can count 5-fold coordinated. Here it is 7. Here it is 8. So whether it is 5-fold coordinated or 7-fold coordinated or 8-fold coordinated, it's crucial. How do you determine that? Experimentally, it is extremely difficult. Let me just tell you. Name me any characterization tool. You cannot get it. There is one tool which you have, and it is called the X-ray standing wave. I do not know how many students know it. Read it. X-ray standing wave is something which is probably the only tool which is available, which can tell you what is the structure at the buried interface. It was done in Hamburg, okay, in those days, okay, and we found, interestingly, that nickel disilicide silicon and cobalt disilicide silicon, both we saw, and we came to the conclusion that nickel disilicide silicon is 7-fold coordinated and cobalt disilicide silicon is 8-fold coordinated. And this result was consistent with the experimental result which was obtained by Raymond Tang in Bell Labs in those days. Okay, so again, here is a matter of details. So it's a very detailed this thing, but I will not go into very much details, excepting to tell you that the 7-fold versus 8-fold, look at how the orbitals in a 7-fold and versus the 8-fold, can you see? Pictorially, you can see the difference between a 7-fold and an 8-fold. And interestingly, the what we observe is the following. Sorry. Yeah, there are two different kinds of whether it is 7-fold or 8-fold coordinated. There are two different types of interfaces. Let's consider nickel disilicide silicon, which is 7-fold. We know that from experiment. What have I drawn here? This is the cross section we have drawn for the charge density contour. Can you see the difference? What is the difference? This is nickel disilicide charge density, and this is the good old silicon, the covalent bond. You can see that covalent bond of silicon 111. Here also it is same. So nickel disilicide and silicon, but something is different at the interface. What is that? In one case it is called A-type interface, where you have got the silicon 111 like that, and nickel disilicide is going in the A-type. The other one is where silicon is as it is, the nickel disilicide is just 180-degree rotated, and that is what it is. So nickel disilicide is 180-degree rotated in B-type, and in A-type it is not rotated. Why am I showing this? Interestingly, we find that the Schottky barrier height for these two changes by as much as 0.15 electron volt. It's a huge number. It's a huge number for a device physicist. For a device physicist, 0.15 electron volt is a huge number. And nobody could understand why. Because we are not changing the semiconductor, we are not changing the metal. So the metal is same, semiconductor is same, only the orientation is different, and we are getting a change in the Schottky barrier height. Why? And this is something which we we discussed using density functional theory, and we got the answer. That's the interesting thing. Okay, so it's a matter of details. Again, the how the perturbation is dying down asymptotically into the individual solids, and it is different between A-type and B-type. Okay, and the interface induced dipole. So this is the pure quantum effect. The interface induced dipole at the heterojunction is something which plays an extremely important role in determining the P-type Schottky barrier height. So basically, it is the density functional based Fermi level minus the density functional based valence band top. plus the delta VXC is the change in the exchange correlation functional when you go to plus infinity and minus infinity. Okay, so this is something which we estimated with great accuracy, and we did find out the difference between the A type and the B type Schottky barrier height, the difference of 0.15 electron volt we could find out. Okay, much later we worked on similar systems, but using what is known as the coincidence site epitaxy. Now, this is again the experimentalists, they know coincidence site epitaxy means it is not lattice matched, lattice mismatched. But then what do you do? In a lattice mismatched interface, what you do is that at the interface, you force the metal to have the same, lattice parameter as that of the substrate, but adjust it when you go along the Z direction. And this is something which we did for silver overlayer on silicon 111. Remember that silver and silicon, they don't lattice match. Unlike the previous example, okay, they don't lattice match. So we did the first principles electronic structure of coincidence site epitaxy silver silicon 111 interface. This was published sometimes in Physical Status Solidity. Okay, so again we did the detailed calculation. Look at just the numbers I would like to tell you. The estimated p-type Schottky barrier height which we got for this system is 0.5 electron volt, whereas the experimentally determined values are 0.54 and 0.56 by two different groups. So that is a reasonably good, very good, I will say, matching. Okay, so the estimated work function values as well as the estimated p-type Schottky barrier height both agree well with the experiments. Okay, now I have to ask for the timings.
About 20 minutes.
20 minutes, okay.
But
so
maybe 5 minutes of that will be questions.
Okay, fine. Yeah. Now we have, when I told you about this density functional supercell approach, and since we got a reasonably good success in case of a metal semiconductor interface, we thought that why not we try to use the same machinery for other things, and we went to metal ceramic junction. Now, when I come to metal ceramic junction, let me just tell you, it is very important for advanced ceramic applications. Okay, advanced ceramics has got a huge application in industry, but unless you have got a metal, what is it called? I mean, a metal. You have to join the metal in order to get the current out. Okay, so the metal ceramic junction is very, very important. So now this is an example of a metal ceramic interface bonding between silver and magnesium oxide. As you know, the magnesium oxide is a large band gap insulator. It's an insulator. Ceramic. Silver is a metal. Why am I showing you this thing? This is also a reasonably good interface, okay, between silver and magnesium oxide. I'll tell you the story. The story is that we were asked to, see why some of the experimentalists approached us and said that, look, when we are trying to put that silver, after some time, the metal was peeling off. That means what? The bonding was not good. Why? We did a very detailed calculation, and we found, I'll just tell you the result, that the adhesion on ceramics like Al2O3 or magnesium oxide, okay, changes as we go from silver to copper to nickel to iron. Why? So this is a ceramic. On that you are putting some metal in order to take the current out. But if it peels off, then it is useless. So you try to do silver, copper, nickel, and we found that as a function of the D band occupancy, okay, we found that silver on magnesium oxide is something which is bonded predominantly as an ionic bond, whereas titanium on magnesium oxide is predominantly a covalent bond, and the covalent bond is stronger. So we suggested to the experimentalists that you try, instead of silver, try to put some titanium based alloy. They did it, and the result was found to be successful. I mean that the titanium based metal on the magnesium oxide was found to be better suited than silver. Okay, when we use in our printed circuit board, the thing, with this thing. We use a silver alloy. Instead of that, here it is titanium. Okay, anyway, so these are all computer simulated images and blah, blah. This is the cross-sectional, the charge density contours, but these are matter of details. Very briefly, I will tell you about the heterojunctions in 2D. So as you know that 2D has got a huge variety from graphene to silicene to hexagonal boron nitride to layered transition metal dichalcogenides. It can be a conductor, it can be an insulator, it can be a semiconductor. And we have all discussed in this meeting a huge lot on all of these. Okay, so what about their sandwich structures? That is the growth of one above the other, the van der Waals heterostructures, that lead to new functionality in electronic devices due to novel substrate-induced screening. This is something on which a large amount of literature already exists. Now, we do it because we have got more freedom to make devices due to the absence of lattice matching constraints. We don't have the constraints of lattice matching anymore in the 2D. And there are dangling bond free interfaces and tunable stacking angles, etc. Okay. So just one example I will tell you, which is definitely something to do with the bonding at the interface. So the HBN monolayer on nickel 111. Okay, this is some paper which I don't remember which year, sometimes around 2015 or so, I think. Yeah. So what happens, I will tell you. When we bring oxygen, this is oxygen, on HBN freestanding HBN, hexagonal boron nitride, and we bring oxygen. It does not stay, it goes away. We have done it by molecular dynamics. It does not stay, it does not like, the oxygen does not like the freestanding, this thing. But lo and behold, when we put the same hexagonal boron nitride on nickel 111 substrate, incidentally, nickel 111 substrate and HBN has got the same lattice matching. So when you put that and then you try to bring the oxygen, it remains. Why? What's the reason? Freestanding, it goes away. Whenever you are putting it on nickel 111, oxygen gets absorbed. So there must be some substrate-induced modulation of electronic structure. Not only that, is something even more. That is, that is this oxygen, not only that the oxygen stays, but the oxygen distance gets a little bit elongated. The normal oxygen distance, whatever it is from your literature, if you look at this oxygen distance is 1.51. It is slightly more elongated than the oxygen distance in O2. Okay? That is what the chemists call activated surface. And this oxygen distance elongation is something which helps in, see the next slide. Very interesting. Now we try to bring a carbon monoxide. This is the carbon monoxide. And this is oxygen, which I already showed you. And this is elongated, it is activated. Now this carbon monoxide comes and takes up one oxygen and becomes a CO2 and goes away. The remaining oxygen, which is remain here, the next CO comes, takes out the oxygen, and both the CO2s are going out, and what remains is a pristine hexagonal boron nitride on nickel 111. This is a glaring example of oxidative catalysis. So catalysis is that. What is catalysis? That it does not take part into the reaction, but it helps, and that is what it has happened. So you have successfully converted CO to CO2. CO is dangerous. CO2 is not. So there are mechanisms like ER mechanism or Langmuir-Hinsfeld LH mechanism. The chemists know it very well. But being a physicist, I poked my nose and tried to see why it is happening like that. So the moral of the story is that this hexagonal boron nitride, when you are putting it on to a nickel 111, there is an interface which is created. And that interface has got a charge transfer. Because of the charge transfer, the ionicity of the boron and nitrogen is something which gets changed. And that is what helps, in the catalysis. It's very interesting. Okay, if you are interested, you can have a look at that. This paper, where is it? Yeah, HBN monolayer on nickel 111. So in your car, at the end of your car, when the carbon dioxide or carbon monoxide comes out, if you put a HBN on a nickel 111 as a filter, the carbon monoxide part will become converted to CO2 and come out. So that is what is the beauty of this kind of a thing. So electronic structure helps. Okay, so now a brief pause. Yeah. So I think if I have a 10 minutes time, then I will now tell you a brief pause and for a change of gear. It is really a change of gear now. So now let us try to go into. In 2022, I came back from IIT and I joined this institute, which is Research Institute for Sustainable Energy, RISE. Okay, it has got many different things. The main thing is the development of batteries, which is lithium and sodium ion batteries using cost-effective solid electrolyte. And many other things we do. You are most welcome to know the details about this RISE lab. But interestingly, the electronic structure, molecular dynamics, transport studies in electrodes and solid electrolytes are being done routinely out there, and the property prediction using machine learning coupled with DFT. But why? Okay, so again we find that the electrolyte interfaces in metal ion batteries play an extremely crucial role. Once again, interface. Now, the structure, these interfaces are far more complex compared to whatever I showed you so far. These interfaces, the electrolyte, are far more complex, involving solid liquid or solid solid in solid state batteries junctions that are not in thermodynamic equilibrium. Evolution, a crucial aspect for the formation of solid electrolyte interface, a passivation layer arising from the degradation of electrolyte. Very difficult thing to handle accurately. The same kind of accuracy that I talked about so far. Challenges, they suffer from severe challenges like volume change, dendrite growth, and chemical decomposition of electrolytes. We are not facing those in our semiconductor interfaces. Dynamic nature, the most treacherous thing. The interface is not static, it changes during cycling. So yesterday, Tanmoy, my colleague, he gave a talk where he showed, what happens when the lithium ion goes from cathode to anode through the electrolyte and comes back during charging and discharging. So this is the interface that is produced is with fluctuating electrochemical potential influencing ion transport and interfacial chemistry. This is dynamic interface, unlike the ones which I showed so far. So the interface between solid electrode in all solid state batteries are way too complicated, okay? And there the theory and modeling that needs to be done in order to compare with experiment is a real challenge. And for handling such complex interfaces, computational tools need to be extended beyond DFT and molecular dynamics to machine learning. So why we need machine learning? That's what I wanted to give you the motivation. So we do DFT, we do molecular dynamics, but over and above that, we do AIML using machine learning force fields to bridge the classical and quantum force fields. Okay, we do MES MP and MES OMAT. These are materials project and that. So the people who are doing machine learning, they probably are aware of this, and we use the active learning loops. So we have got in our group already, the expertise. Tanmoy is here. Biplab is also here in this conference. So we have done the DFT plus MD study to identify diffusion pathways in halide solid electrolyte. Li3YCl6 is a halide electrolyte. Remember that electrolytes can be either halides or sulfides or oxides. They have all got their own, advantages and limitations. So Tanmoy has done a lot of work on this Li3YCl6, where what has been done is that we are basically interested in optimizing the ionic conductivity of lithium. So why yttrium is alloyed with different transition metals in the 3D series, and that's what has been done. You see here the yttrium is alloyed with titanium, vanadium, chromium, manganese, blah, 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 up to copper, everything. And it shows the diffusivity as a function of inverse temperature. You can see that, okay? And indeed, DFT helps us to identify some of the candidate compounds apart from the pristine parent Li3YCl6. And we have also done the classical molecular dynamics, okay? Whatever you are seeing, the puddles, these are nothing but the lithium going, from the cathode to the anode, okay? And the molecular dynamics is showing you the 3D lithium diffusion pathways as shown by the gray tube. These gray things, these puddles, whatever you are seeing. And these are the lithium and yttrium and the transition metals atoms, okay? So this is a snapshot which shows how the lithium is actually going from cathode to the anode. And the details is given in this paper which we published, optimizing solid electrolytes with 3D transition metal doped Li3YCl6 for lithium ion batteries. So these are my colleagues, and Ovik is an experimentalist, and yeah. Okay, so more recently, in one of our students, Rajdeep, he has done some on-the-fly machine learning force field, which has the advantage that we need not do a detailed, expensive density functional calculation. We can do what is known as the on-the-fly workflow, okay, which we can do. And this paper has just come out, I think, last week. Last week it has come out. Emergence of a frustrated configuration in Li3YCl6 solid electrolyte, an active learning approach. This Tanmoy has taken the leading role in this thing, and Rajdeep has done the calculations. Okay, this is a matter of details. I have to skip. No time. So the AI plus DFT integrated framework is something which is here to stay, and the physics-informed deep learning for voltage prediction has been done for using high-quality data sets, featured engineering, and what is known as the FCDNN approach, deep neural network kind of a approach, okay, which we have done with reasonably good amount of success. And that is shown by this graph here, where the voltages are whatever predicted by our AIML approach, and the full DFT calculation that has been compared, and it is look at the R square value and the MSE. R square is 0.99, MSE is 0.012. This is an excellent agreement in capturing the electrochemical behavior. This is for a sodium ion. Okay, we have done it, and here is a detailed numbers, okay, for that. LiCO2 is the one on which the Nobel Prize was given 5 decades ago on batteries, and there are many others candidate materials which we have now, and these are the experimental values, and these are our DFT values, and these are our FCDNN values, okay, and the prediction of FCDNN is a reasonably good agreement, and this came out in small just recently, integrating density functional theory with deep neural network for accurate voltage prediction in alkali metal ion batteries. So the DFT and FCDNN approach is okay. We have developed a scheme by combining high throughput data, fully connected deep neural network. FC stands for fully connected deep neural network, and selective DFT checks, and our approach offers an efficient and robust screen then validate workflow. And this was done in collaboration with IKSC in Bangalore, the India-Korea Science and Technology Center. Shatodeep, my colleague, he has done the work from there, and we have collaborated. And this came out in the news, the Korean news item, because it is the India-Korea Center. They came up with new AI-linked sodium batteries possible, something in Korean. Okay, and here also we have come up with a major leap in clean energy innovation. This is the Indian news item. This is the Korean news item in KIST and RISE. Okay, so the last example, that is something which is the ongoing work which is going on lithium LLZO interface. Again, interface. So this is the LLZO is something which is a typical standard, electrolyte, and lithium is a standard, electrode. So how to handle this electrolyte interface using latent space active learning? This is done by a you know, undergraduate student, Mehul Darak. And our goal is to develop a scalable machine learning interatomic potential for that LI-LLZO interface and capture the interfacial diffusion, reconstruction, and defect-driven phenomena. And we have generated the data, and we have done the so-called mesh architecture, and so on and so forth. And this is the active learning loop. Because of the lack of time, I cannot go into, but this paper is just going to come out pretty soon. I hope so. Okay, so the DFT is accurate but cannot scale. So single interface supercell requires huge number of atoms. So we go to the alternative of universal machine learning interatomic potential using MES MP or MES OMAT, etc., etc. And the universal MES OMAT, if we do it, and the values of the energy and the force that we are getting is something which can be tuned to the numbers. Compare the numbers. We have improved like anything. And very recently, we are now trying to put a external bias, because batteries have got an external bias. I mean, there is a electrode from cathode to anode. There is a bias. So we have put the external bias and tried to see how the solid electrode electrolyte interface behavior works under the external bias. This work is in progress. Okay, so what is the take-home message? Integration of AI-driven approach and high-throughput DFT computation leads to an efficient, low-cost materials discovery and ready to take up challenges of complexity in handling next-generation smart materials. We proposed a series of new layered oxide cathodes with different kinds of, this is a matter of details. IKST RISE team has developed a unique DFT plus FCDNN workflow that can accurately predict the operating voltage of battery materials, thereby paving the way for faster discovery of next generation sodium-ion battery. And such AI-guided design will be critical for bringing sodium-ion battery seen as a strong, low-cost complement of lithium-ion battery. This is all over the world, people are doing it. And we are developing the machine learning interatomic potential. So combining this deep learning approach with high-performance computing marks the beginning of a new era in material simulation of batteries. So we have got a lot of things in our wish list, but the most important thing is the last line, namely use more earth-abundant materials. Sodium is way more earth-abundant than lithium. So use more earth-abundant materials for cost effectiveness and sustainability. That is our goal. Okay. So what is our concluding remark? I have tried to give you a flavor of how DFT can be used as an ideal tool for investigating various kinds of interfaces. I told you about metal semiconductor, Schottky barrier height. I told you briefly about the metal ceramic bonding. I told you about the 2D materials, heterojunctions, and last but not the least, I told you about the battery electrode and solid electrolyte interface. Everywhere, the interfaces are playing a very critical role. That's the subject matter of my talk. And I must tell you that Herbert Kromer, in his Nobel lecture in the year 2000, gave this very interesting phrase: interface is the device. Interface is the device. Without interface, you cannot think of a device. Okay, so collaborators, I must say that I learned a lot of things by discussing with my colleagues in Max Planck Institute, Ole Andersen, Peter Blöchel, Niels Christensen, Ole Gunnarsson. And of course, I learned a lot by interacting with my students and postdocs who contributed immensely to the 4-decade-long journey, which I tried to say. I gave you references of 1989 PRL, and the latest one was last week. So 89 to 2026, how many years?
37 years.
Whatever, 40 years, 4 decades long. The journey is something which is truly exciting. Okay, and these are my current collaborators from IKST Bangalore. Shatodip Tanmoy is my colleague in TCG Crest. Rajdeep is our student, and Biplab is collaborating with us. Biplab is from Uppsala. He's here. And Mehul is in IISc Bangalore. He's a undergraduate student. Funny is is really a workhorse in terms of the large-scale, exascale DFT computation, and Karthik is one of the smartest PhD student who did the work combined with Funny and of course partly with our group. So. And then, of course, I must say that our TCG Crest is a vibrant group. Look, all these youngsters, we have fun there. So you are most welcome to come to our TCG Crest and interact with us, okay, with our group. This is the last one, the epilogue on a battery roadmap. I told you about the battery, but it's a fascinating chemical ballet between lithium ion and sodium ion may result in batteries showing both high performance and sustainability. Lithium, high performance, sodium, sustainability. Okay? So, such coexistence of lithium and sodium in battery obeys our century-old Oriental culture that have their own foundational equivalent representing the same dualistic interconnected forces of the universe. Interconnectedness and interpenetration. You know of Hatha Yoga. In India, what is Hatha Yoga? Ha means sun and Tha means moon. The same thing is there in China, yin yang. Same thing in Korea, yum yang. In Japan, yin yo. Everything is nothing but balance and harmony. Sun and the moon. You see the balance and harmony of opposite forces. So lithium and sodium can coexist, they need not compete. That is where I end. Thank you very much.
Thank Professor Das for a fascinating overview of application of DFT and more advanced techniques to interfaces. We have time for a few questions. We'll start right there. Yeah, you want to? Yeah, you may go now.
Thank you very much, sir, for such an amazing talk. I must say it is one of the most amazing talks I have ever heard. And I have one comment as well as one question. So first, let me start with the comment. Like you have already introduced on the flight training, being a former postdoc from the developing team itself, I want to mention to the team, means to the students sitting here, that on the flight training can handle up to 20,000 atoms. So on CPUs only. Another thing is it becomes heavy when you take more than like 3 type of atoms. So tomorrow I'll be going to discuss on the flight training in more details. Now let me move to the question. Suppose if you want to make an interface of 2 different crystal structures, say cubic and hexagonal. So can you please suggest what should we need to take care of if you want to handle it with machine learning force fields only?
Oh, that's a very good, very relevant question, I will say. Okay, so in order to handle it, first of all, as you know, for a DFT calculation, you have to generate a kind of a supercell. Okay, it doesn't matter if the one side is cubic and the other side is hexagonal, let us say. Okay, but remember, I must say that silicon nickel disilicide, when I said silicon is actually what the interpenetrating FCC, but it's basically a diamond structure, right? Okay, and nickel disilicide is cubic. But when you put silicon 111 and look like that, basically that is matching with the nickel disilicide cubic. Am I clear to you? When you look at the 111 direction of silicon 111 and then on that you put the nickel disilicide, there is a perfect lattice matching. Okay, coming to your question regarding how to handle it in the ML, I mean machine learning interatomic potential.
We can handle it with EFT, we can handle it with ML.
Exactly, that's what I'm going to tell. So we can handle it, but for further discussion, I can tell you some more details about it. But it is the binary answer is yes, we can do it. Yeah.
Maybe I'll discuss.
Okay, we can discuss. Yes.
Thank you.
There's another question back there. Yeah, please.
Very nice talk, sir. Sir, I want to ask, you mentioned about the finite element density functional theory, and it can handle the very large number of atoms, huge number of atoms.
Yeah.
To DFT. So, in a nutshell, can you explain me what is DFT conventional codes doing wrong, which you corrected in order to scale the DFT so much.
Okay.
First question is that, and second question, small question is that, like you were saying, accuracy is not hampered in doing so.
No.
It is as much as accurate.
Yeah.
So, what are the parameters, physical properties which we generally check for the benchmarking in between these two methods?
Okay. The first question first. Okay. So, density functional theory is basically a differential equation. You have to solve it. You cannot solve it exactly. Analytically on a piece of paper, you cannot do it. You have to do it using what is known as a self-consistency cycle. This you know, all of us know that. You have to do it self-consistently, okay? Now, for that, you need a basis set. Without that, you cannot proceed. Why? Because the wave function you have to expand in terms of a basis set. Now, we all, I mean, the people who are, even the experimentalists here in the audience, they routinely use WASP and then quantum espresso, Gaussian and blah, blah. Many people different. Now, everywhere the basis set that you are using are different. Now, there is, so some basis sets are suitable for some materials, not for all. For example, if you take, say, silicon-based system, then your plane wave is fantastic. Okay, plane wave basis set. But if you try to use a molecule where there are localized, a molecule, there a Gaussian works better. But Gaussian and plane wave, they are completely two different animals. But they are two different basis sets. They have got their own advantages and disadvantages. The chemists like to use Gaussian because they work with molecules. The physicists like us try to use, plane waves, which most of the people use. But the problem is that plane wave is democratic. Plane wave is something which is having same weight everywhere. Whereas here in our finite element basis, when we go from the site of the atom outwards, there's a polynomial function which we try to fit so that when it is not identical, and when you come close to the site of the atom, the mesh is different. When you go away, the mesh gradually becomes more and more sparse. So as a result, what happens is that you get a much better accuracy there. And that is why I said, without losing the accuracy, I have compared the numbers which we have got using quantum espresso and DFT-FE, identical up to certain level. But for bigger cells, the quantum espresso conked off. It did not give me anything, even with the biggest supercomputer. I did not get it. So, but there, DFT-FE gave me a number. So I come to the conclusion that DFT-FE is better suited. But if you want to know further details, the GitHub I gave here, but if you are interested, I can give you. Okay, there all the details are given. Okay, how the DFT-FE can be used meaningfully for things which are periodic, non-periodic, or even semi-periodic like quasicrystals. We can discuss.
One last question, perhaps? Yeah.
Follow-on question. So you said DFT-FE gives very good results for larger number of DFT-FE.
Yeah.
So but what do you compare it against to benchmark it?
See, okay. See, what we have done is the same system for a smaller unit cell. Okay, we have compared with the conventional basis sets like plane waves, which everybody uses.
So that I understood, but I'm saying when you go
beyond
to the larger planes,
there is no way.
There is no way.
There is no way, because we don't have a tool. Okay, we can use things like tight binding. Okay, with many people, but tight binding is not first principles. Tight binding is something where we take the some of the numbers from the experiment, compare it, and we do. There we go to. But here, this is all ab initio, first principles calculation, without resorting to anything like a parametrization. No parametrization. It's completely ab initio.
We have perhaps one last question.
So actually, you were talking about only flight training. So basically,
Only
flight training.
on the fly.
On the flight
Yeah.
training. So basically, you were just validating your neural network predictions using the actual training data from the DFT at several steps. But basically, I stand from the only flight training.
Yes.
Yes.
Yes. Yeah. Tell
When
me.
I think about it, like neural networks or other AI models, they just predict the pattern. basically they work on prediction of a particular pattern.
Huh.
Now, if you think about the thing like this, like I have a continuous phase transition from solid, liquid to then a gaseous state. Now, if you train a neural network, particular in this particular stuff, then it can never predict something like sublimation. Because these things will be directly predicted from your actual equations. Now, if I just reduce the temperature variation, so it would be very difficult for on-the-fly training to capture a sudden change in the phase or a dramatically changing event in a very short period of time. So that is the basic difficulty for them.
Yeah,
so
that is true. No. We do not go to the whatever you said, the sublimation or the gaseous state. We really don't go to that. And she will be able to tell you something more. We do not go into that. We go up to a certain temperature. So we are still in the solid phase.
No, sir, that's right. But what I'm saying that this is just an example. Like something can just happen in a short span of the change of the variables. That is something that this can't predict. The actual equations will predict that, but this particular technique will not predict. So what you are doing to find those particular things?
I think it needs a little bit
I think
more
this
discussion.
should go on, but maybe
We'll talk about it. Yeah.
Perhaps one last question.
Very nice talk, sir. Sir, I just want to ask you, when you mentioned CO oxidation from monolayer HBl on a nickel 111, have you done a similar experiment with copper 111? And if you...
That's again a very relevant question. Yeah, you are right. I mean, copper 111, copper and nickel, by the way, in the periodic table have very close lattice parameters. Yeah, you are right. Copper, we have not done as detailed as nickel. There is a reason for it. Because in copper, the band is completely full. It is 3D10 4S1. Okay, the D band is completely full. In nickel, it is not still full. Okay, so what happens is that we have seen that when you are putting the boron nitride on the nickel 111, there is a charge transfer from boron and nitrogen both with the substrate. And as a result, the ionicity of the boron nitrogen in the plane, that changes. Now, suppose instead of nickel, we use copper. First question is that we have not done the detailed calculation on copper, but some rough calculation we have done, and we have found that there, unfortunately, the boron nitrogen ionicity is something which is not changing the way it is on nickel 111. And unless it changes, it will not have the oxygen thing coming there and getting so copper is not. So basically everything depends on the electronic structure. Copper and nickel, but from structural point of view, yeah, both are same. But we have seen that in case of copper, if you put boron nitrogen, it does not work.
The activity of D shell is...
Yes, exactly.
Well, I'm sure this discussion will continue endlessly because of Professor Das's inspiring lecture. But I think we should now conclude the evening program and thank Professor Das again for a fantastic lecture, which was really educative for all of us. Thank you so much.
Thank you very much. Thank you. Thank you. Thank
you. Thank you, Sanjay, for chairing this session, and thank you, Professor Das, for a wonderful colloquium.
Thank you very much.
And there is a memento for you from the organizers.
Thank you.
Professor Sanjay Puri will hand it over to you.
Thank you so much.
Thank you very much. Thank you, Sanjay. It was really a pleasure. Thank you so much. Wow.
Maybe you can pull it out and take a picture, I think. Yeah.
Oh.
They might want to take a picture. Oh, how lovely.
Oh.
Tree of knowledge.
It is a tree of knowledge. Thank you, Sanjay. Thank you very much. Yeah.
And Sanjay, there is something called
yeah.
Satyavrata has been very generous about,
How lovely. Thank you so much.
Thank you.
So let us conclude today and